In the last two videos, we've talked about this classifier framework for text classification and about modeling, focusing on linear models. This video will focus on learning. Given that we have a way to define a score function, learning is about using data to choose weights. There are many ways to think about learning, and you would see several of them in a machine learning course. Since our time is limited, we'll focus on a single framework, that of empirical risk minimization. This is the most widely used supervised learning framework in NLP and combines ease of use with effectiveness and applicability to a wide range of applications. We'll introduce it in this video, but return to it later in the course. We're going to start by defining a cost function. This is a function that compares two output labels, typically a predicted label and a gold standard. So it's a function from a pair of labels to a non-negative scalar. We can think of it as telling us the cost of predicting a label when the gold standard is some other label. The idea is to define this function to be as similar as possible to the evaluation metric for your task. We assume a few conventions such that the cost of a label when compared to itself is 0, and that the ordering of the two arguments doesn't affect the output. So what cost function should we use for classification? Probably something like this, which returns 1 if the two labels are different and 0 if they're the same. However, that may not always be the best choice. Suppose we're doing 5-way sentiment classification with these labels. When we evaluate classifiers for this task, we may want to treat different error types differently. If the gold standard is very negative, then classifier that predicts negative is better than one that predicts very positive. And the cost function can be defined appropriately to reflect this. Now, given a cost function, we can define risk minimization. Say we're given a training set of xy pairs where yi is the gold standard classification label for xi. We assume this data is drawn IID, that is, independently and identically distributed from some probability distribution p of x and y. We then want to solve this optimization problem, in which we're choosing the weights w that minimize the expectation over xy pairs of the cost of the classifier's prediction. As a reminder, the classify function returns a predicted output for the given x using weights w, and then the cost function tells us how different that predicted output is from the true output y, which comes from the joint distribution. However, we can't solve this optimization problem directly because we don't know the true distribution over xy pairs. So the idea of empirical risk minimization is to replace the expectation with respect to the unknown distribution with a sum over data points. However, there's still a challenge with this. It's actually intractable to solve this optimization problem, even in the simple case of binary classification with linear models. So let's generalize this objective function. Instead of the cost of the classifier's prediction, we're going to write it as a loss function that is a function of the input, the gold standard output, and the parameters. Then we'll refer to the cost of the classifier as the cost loss. This is often called the 0-1 loss. The cost loss is difficult to minimize, so our solution will be to replace it with a different function, often called a surrogate loss function, that is easier to optimize. Why is this function so difficult to optimize? Well, it may not even be continuous. If you recall, the classify function contains an argmax. As we make small changes to the parameters w, the argmax may change suddenly to be a different label, which may have a different cost. So the loss may jump around. This means we can't use gradient-based optimization, which we'll talk about more in the next video. So we'll discuss a few surrogate loss functions that are continuous. Here's a loss that I'll call the max score loss. Minimizing this loss will make the score of the gold standard label as large as possible. This is a continuous function, there's no argmax in it, but it's a bit naive. It's unbounded, so the loss can go off to negative infinity, and therefore learning will never converge. So our first realistic surrogate is the perceptron loss. It's so named because it can be reverse engineered from the perceptron algorithm, a classic learning algorithm with simple guarantees. The next loss we'll talk about is Hinge loss, which resembles the Perceptron loss except for the presence of this cost function within the max. Hinge is well known as being the loss function underlying support vector machines and large margin learning more generally. It can also be shown to be an upper bound on the cost loss. To get some intuition for these loss functions, let's look at a visualization for a single input x. Suppose we have a label set with 5 possible labels, shown here as y1 through y5. We can use our model to compute the score for x paired with each y. So the height of the third bar, for example, is the score of x and y3 using parameters w. We can also visualize the cost of each possible output when paired with the gold standard. The gold standard has cost 0, so it's y5, and the other bars are the costs for those labels when compared to y5. We can also plot score plus cost by stacking the bars. Now let's consider how minimizing each loss function will affect these scores. First, the max score loss, which only looks directly at the gold standard output. What is the effect of learning, that is, minimizing this loss function for this particular input x? Well, the score of the gold standard label will go off to infinity. The scores for the other labels may be affected too, depending on the weights. Now let's look at the perceptron loss. When we minimize this loss, we're trying to increase the score of the gold standard and decrease the score of the model's highest scoring label, which is y3 in this example. This loss has a minimum value 0, which is reached when the gold standard output has the highest score. Hinge loss again seeks to increase the score of the gold standard, but now instead of decreasing the score of the highest scoring label, it decreases the score of the label that maximizes score plus cost, which is y1 here. This is a label that the model likes, but has high cost. The loss reaches its minimum value of 0 when the score of the gold standard is higher than score plus cost of all other labels. Remember that learning affects w only, which affects the score function. The cost is an intrinsic property of a label and is not affected by learning. Let's look again at these different loss functions. With cost loss, all that matters is the argmax label. So the loss may be unaffected by transformations of the weights if they don't change the argmax. That is, the values of the scores themselves don't matter as long as the argmax stays the same. Unlike the perceptron and hinge, where the scores themselves directly affect the loss, even if that doesn't change the argmax. For example, if our score function is a linear model, then we can multiply the weight vector by any positive constant, and the cost loss will be unaffected, while the perceptron and hinge losses will be affected. What's concerning is that there could be cases where we can get a smaller loss by simply scaling up the weights in magnitude. This can lead to overfitting in practice. We may reach a very low loss in our training data, but the model may not generalize well. Therefore, it's standard practice to add a regularization term, RW, to the objective and do regularized empirical risk minimization. This regularization term is a function of parameters only. It doesn't depend on the data. There's often a tunable hyperparameter, shown here as lambda, which represents the strength of the regularization term relative to the loss. The loss term helps to fit the data, and the regularization term helps to avoid overfitting to the data. Two common choices of regularization functions are shown here. L2 regularization corresponds to using the sum of squared parameter values, and L1 uses the sum of absolute values of parameters. They both help to avoid overfitting by penalizing large parameter values. L2 is smooth and more widely used. L1 is not smooth but is continuous and convex, so it's subdifferentiable, and it also tends to lead to sparse solutions, in which many parameters in the learned model become 0, which can be helpful for reducing model size and increasing interpretability.